So, some of you have seen part of this on Wednesday, ICFP. I'm going to try to go a little bit more in detail to kind of give a feeling, give you an intuition of how it works and why it works or doesn't work at some points. So, as the title says, I'm building a just-in-time compiler. Why am I doing this? Well, there are certain problems with the static approach. So GHC is a great static compiler, but sometimes there are some issues which are due to it being a static compiler. So one big problem is we have like these ways of compiling things like profiling, HPC, vanilla is the standard way, and that means that we have to recompile everything multiple times, and well, that becomes a bit of a problem even for some, for example, the platform binary is like 100 megabytes or something. The other thing that I thought you could maybe attack with this is to get maybe more predictable optimizations in like your hotspots. So GHC currently doesn't have any kind of feedback directed compilation optimization, so it kind of does its best thing, and I think that was yesterday in the discussion, like tell me how to make GHC, the inliner, like optimizations working in one version of GHC but not the other because there were tiny inliner changes. So the idea is that if we can do optimization at runtime, we can maybe be more predictable in applying optimizations when they come. I've chosen to use trace-based just-in-time compilation, and those who are familiar with this know that it was mainly used in dynamically typed languages. And it turns out it's actually quite useful for Haskell as well, because the Haskell execution model has some things which are very close to what a dynamic language, or what a optimizer for a dynamic language has to do. Particularly these are dictionary lookups, overloaded function calls, and evaluation of thumbs. So the idea of a trace-based compiler is, instead of trying to compile a control flow graph as one thing, it only traces through follows the execution of the program and compiles only those hot paths through the program, and then turns that into a linear sequence of code. And in fact, you can even get a slight bit of, in some systems they actually use just tracing for the locality advantage. So because all your code is now straight line code. Now, if you, do we have a click in this one?
Your pointer.
Your pointer. So, so in the original program we had some control flow here. And of course, we have to kind of allow for the possibility that this control flow this part might be taken later in the future. So we start, we have to add a check here. So at this point, the program isn't much faster, but only due to locality. But what we can do now is we can see things and optimize them down here, and usually we can do some speculative optimization. So for example, if something is allocated here, then it might escape here, or it might possibly escape here, but we assume it's not going to happen, and then optimize it away. And then we kind of say, only if execution actually leads down one of those paths do we need to do the allocation. And if we build good traces, then we can remove, for example, lots of allocation. And because we kind of specialize on the control flow, we also automatically inline, we also automatically specialize on the particular types that we use. So yeah, this is what I mean. So if you have evaluating expression, execution might continue in various places in the code. In practice, it's not that many though, but it depends on the call side. GHC exposes this by doing inlining. Supercompilation does something very similar, but statically. And the idea is very similar. You could say is I'm trying to do a little bit of supercompilation in the parts where it counts. So I decided not to do this directly in GHC. I figured it might be easier to start with a clean slate. I did steal a lot of ideas from Luajit and some code. And so one point, for example, I'm not using GHC's bytecode interpreter. So I'm compiling to bytecode, but I'm not using GHC's bytecode. Why is that? GHC's bytecode is, well, there's actually some research into bytecode interpreters, into pure bytecode interpreters, and there's some fairly recent work which showed that if you use a different style, so the standard interpreter says push argument, take the two arguments and put it back onto the stack. This is actually quite slow because each of those instructions, the overhead of an interpreter is the dispatch. So if you need to do lots of instructions, it becomes very expensive to execute, and it's actually faster if you have a bit larger instruction which takes its argument directly from the stack and then writes it to somewhere else. And Luajit uses one of the bytecode interpreter which is very efficient and it's like implemented in assembly. It is actually not that difficult, but it's very optimized and very fast. And then, so the idea is, so we send the program through GHC, to the GHC high-level optimization part, and then GHC converts to STG and then CMM, and I convert to my bytecode. So all that CMM stuff I bypass and essentially do at runtime, but in a much simpler way. So the bytecode, so the code is run in the bytecode interpreter with a little bit of profiling to detect these traces, and once we detect the trace, we send like intermediate instructions which are kind of similar to what CMM has to the trace compiler, but it's a linear sequence of code which is extremely easy to optimize. You don't have to do any Hubble style data flow optimizations. And then you compile it, and you have to be able to quickly switch from compiled and back to interpreter code. That's one of the key important performance issues too. So to show you how that works, I have an example. So note if we use GHC functions here, we would get builder, folder fusion, that kind of stuff. But that's a static optimization and relies on inlining, so we can't necessarily do that. But I have here, so I have a very simple, this one generates the numbers from low to high, a list of the numbers, and this one just sums them up. So when we send this to the trace compiler, so this is kind of the execution sequence of this. So we start with sum and a thunk, then that thunk gets evaluated, so we jump into the thunk, where we evaluate some stuff, and then we return a console with a new thunk, then we pattern match on that, and then we loop back. So that's the trace. And beware, this is how it looks like at a low level. Try to add some comments. So, so up here we're loading the first argument, and then we specialize, in this case it was always an integer, so we kind of specialized on this. So this guard says, make sure that this is still the case, otherwise leave the trace. Then we load the second argument, the list, and again, in this case it was a thunk. So because it was a thunk, execution continued executing the thunk. So we kind of implicitly jump into the thunk here. And in the thunk there were two variables in the so the thunk had two free variables, so we have to now load these variables, and then we do the actual, we have a guard for the if that was in the code, over here, and then we need to allocate the first element of the list, need to increment the counter, and then put it back into the new thunk. Then we create a list, and we update the thunk, which came from here, with the result. And then we return to sum. Sum now pattern matches on that thing we just allocated. So you see already some optimization opportunity. and then it takes apart that result, that's this x and axis here, does some unboxing here, so these are integers. I think that might actually be cards missing. Anyway, so we do some unboxing, and then we allocate a new object, which is the new accumulator, write back the new values to the stack, and repeat. So this is what the trace optimizer sees. And there's already, like, we can optimize some of these things. So we just allocate that object, so we can just, it's kind of a known case transformation, but on a low level, so that stuff goes away. This is one of the things that currently inhibits most optimizations. In this thunk here was just allocated previously, no one else has appointed to us, so we could actually throw it away. I currently don't have that information. I can abuse the spec and say, oh, Haskell is defined to be a non-strict language, so I don't have to implement lazy evaluation. In practice, that's not a good idea, but I believe there are ways to, say, dynamically track whether something could be shared, so some sort of pointer tagging, and then you could prove that this one would be unnecessary. And if I remove this, then I can enable a whole slew of other optimizations. So the first thing we're going to do is, so we have this whole loop here, but it's a bit tricky to see, oh, okay, so this value flows back, and can we do something about that? So what you do normally is you kind of separate something into loop invariant code and loop variant code, or in GC, on a high level, we do the worker wrapper transformation, which is very similar. Because we want to have a very fast and simple compiler, what we do is we copy this loop once, renaming it appropriately, and then we can, but instead of looping back here, so we don't do loop unrolling, we do loop peeling. So this is the first iteration of the loop, and these are all the future iterations of the loop. And so we see, so we wrote, so if we go back, this one just reads this value which we just put there, so we can just forward those. Then, so this now becomes a simple substitution, so we can propagate that. Well, accumulator 2 was just allocated as an integer. So that goes away. We have more forwarding going on. This thing we can't optimize away, but so now this is kind of the core loop, and what I mentioned before. Let's assume, because it's a trace, we know it's very frequently executed code, so most likely this one won't fail, which means let's try and do the allocation only if we fall back to the interpreter and try to avoid it on the trace. So if we do that, well, all that other stuff, all these allocations go away, and what we end up with is this tiny loop, and this one here is just copying the new versions into the old versions, and with the register allocator we can make sure it's the same register, and we end up with this loop.
Yay!
So that's so this is our final loop. We have like a less optimized initial start to the loop, and then a very tight inner loop, because we were able to avoid the update. So yeah, that's another explanation of that problem. I have a little time for demo. So can you see that? Oh, yeah, I'm here. Let's run GHC. So this is the same program running 100 million iterations with GHC. So I have to warn you, this is not doing this great level of optimization. This is, so let's run this. This is GHC, running the loop. But you see lots and lots of allocation. That's because GHC currently doesn't have super compilation, so it can't actually remove those allocation on its own unless you rewrite the primitives using build folder fusion to enable build folder fusion. So we get like 1.16 seconds, and allocation rate is down here, 6 point. That's actually faster than again. Okay. So now let's do the same thing with my bytecode compiler, which doesn't yet do this loop unrolling kind of stuff. Well, it did at some point. I had to disable it, but even without that, it's not that bad. Oh, why did it slow? No. So this is the mutator time, and so this is the actual program time, and then we have a little bit of GC time. For some reason, my GC is faster than GHC's, even though it's really simple. I don't know what's going on there, but it's giving the right answer. See, then true. And you see that because I was able to use LuaJIT, the compiler overhead is actually really low, or pretty low. It's like 0.7 milliseconds. So it compiled one trace. So I have another example which both GHC and this it doesn't do particularly well. So all I did is I have the sum up to thing, and I inserted a map plus 1 in between. So I have enum from 1 to 100,000, and each element is added increment by 1. So which shouldn't really be much slower, right? Oh, it's almost twice as slow. So previous one was 1.12 seconds, and now it's suddenly twice as slow because it allocates twice as much data. So if I run that same thing with my JIT, kind of go in a similar ballpark. So 2.5 seconds. So basically this is like the baseline performance, and then I believe we can do some things on top. So the idea is that, but imagine, say GHC didn't inline something and there's lots of function calls. This thing would at least reduce it to this kind of level as if GHC inline thing. And as I said, with update avoidance, we can probably do even better. Right. So before I go with questions, some limitations. Trace selection is currently a bit of a tricky thing. I got some interesting idea from is it here? George. We could probably do something like Leonard's mu and have an explicit compiler annotation, and that would give the compiler a very strong hint to please start a trace here. So maybe a little bit of user annotation could be helpful. And finally, I only implement like a few set of primitive operations. So for example, raise, IOREFs, IO is currently missing, but I don't think there's any important thing that prohibits this from working. Okay, thank you.
Any questions? Is there any?
No, there's a red button.
I think I've pressed, okay. Is there any hope that one day your tool might allow programs to work that use compiled system libraries, so that if you use data byte string is compiled with DHC, and the code uses is running in your JIT? Or is it just too far away, the different runtime and expectations?
Currently, it's, so GHC, I deliberately chose a different execution model. I had some short discussion with Simon Marlowe whether we could whether my execution model really has to be different, or whether, I know that the calling convention is always the stuff. So when you have to handle over application, part application, not all that kind of stuff. All my info tables contain bytecode instead of compiled machine code. So you have to, I think it's easier to model that somehow as a foreign function call. And then there's the garbage collector. So no, I think the only way to do that properly is to really integrate with GUC runtime.
So you mentioned one of the disadvantages of GHC's approach is that sometimes it can be quite unpredictable when your optimizations are going to apply, and if a small change is made to the inliner, then suddenly your program runs a lot slower. Do you think the trace-based approach is going to make that easier to get predictable?
That's the hope, but currently it's like I only support too small a subset of Haskell to run large enough examples to prove that this is the case. But by trying to run little bigger examples, I already noticed that. So these kinds of loop optimizations only fire if you have a constant stack thing, because otherwise you have to write your data to the stack, and you don't know at what point in the future we might fall back to the interpreter, so you can't just rewrite all the stack before you fall back to the interpreter, so you basically have to leave the stack in the state such that it could be consumed by the interpreter, which means allocation. So if you have like the non-tail recursive sum, but the one that uses stack, which you really shouldn't use, but if you use the one that uses the stack, then I can't do the optimization. So I think I have to like tune the heuristics to kind of prefer things, loops that use constant stack, and then if that doesn't work, so I hope so. Well, I don't know. I have no proof yet.
Questions?
Do you literally use LuaJIT? I mean, are you using the same bytecode as Lua?
The same bytecode design. It's different semantics, much different semantics.
Okay.
So LuaJIT kind of say each instruction has 4 bytes. The first byte is the opcode, the second byte is the target, and the next 2 bytes. So the idea is just that I can use the same interpreter technology, but change the semantics. And the same with the intermediate, the compiled intermediate representation. I'm kind of using the same format, but also the semantic is custom.
Right. Just to speak to your earlier, the thing you were saying in a non-tail recursive situation, supposing you have a non-tail recursive function that walks over a tree and produces a new tree, and then that's consumed by some other function. So that's a sort of classic fusion situation. Do you think that you'd eliminate the intermediate tree? So it's not tail recursive,
Right.
But nevertheless, one function is directly consuming the results of another. I was wondering whether you catch that.
So you can, well, so this is like the map example, for example, where if you have the producer, the consumer, and you just stick a map in the middle, you should be able to.
I suppose it is, except that there you have your ultimate consumer was a tail recursive function.
Well, in the end, you always have some sort of consumer. So I think, okay, so if anything is allocated on the trace and dies on the trace, I can optimize it away.
Other questions? Then I have one.
So can we take your improved bytecode and make GHCI faster?
I talked to others with San Malo a little bit. So what I'm actually, so my bytecode actually looks like Grin at the moment, if you know Grin. Except that Grin made sure to optimize array eval and apply by doing like a whole program analysis. I kind of do that lazily by specializing each polymorphic that eval and apply to its use side. So, but it looks a bit more like the classic call something fallback. But what actually happens underneath is very similar to GHC's eval apply thing. So the only thing I'm not doing is generate these call continuation or return continuations. So if we could change the bytecode to do these return continuations, then it should be possible to put that into GHC. But it's a non-trivial amount of work. But maybe another MSI internship or so.
Any last questions? Thank the speaker.